as this. Okay. Now, if the inverse of fx, what is the inverse of fx? Well, we know fx is equal to fy. Therefore, the inverse of fx is equal to the inverse of fy. Right? Inverse that will give you the inverse of that. So instead of fx inverse, let's write fy inverse. Put it here. All right? Well, anything inverse times itself is just the unit. Right? That's what inverses are. So this will just be e of h. Okay? Now, so we've shown that f of x inverse y equals e of h. And what can we assume from that? Oh, that means, so if f of something gives you e of h, it means the something here belongs to your kernel, right, by definition. That's what the kernel is. It's the set of all points or elements in this subgroup that map to the unit of h, right? So that therefore, if this f of x inverse y equals e of h, therefore the thing inside the brackets here, that element, and x inverse y belongs to g, right? But it maps to E. Therefore, x inverse y belongs to the kernel, right? Belongs to the kernel. Now from 46.1, if x, now this is if and only if here, right? So we've got that x inverse y belongs to the kernel. That's here, the right-hand side. Now it's if and only if. So if this is true, we can go from right to left. If that's true, therefore, xk equals yk. Right? So xk equals yk. We're almost there. Now, k is your kernel f, and it's a subgroup. We showed that. But your kernel is a subgroup. Therefore, it's a group. Therefore, it has a unit. Right? So one of your elements here will be, now this is a coset, right? That's a coset. So one of your elements in K, which is now a group, right, will be the unit, E. So one of your members of this coset, which is still just a set, will be X, because of XE. Okay? So X will be a member of that coset. And by similar reasoning, Y will be a member of this coset. But these two cosets are equal. So that means X belongs to this coset and Y belongs to this coset, but they're the same coset, right? Because they're equal. Therefore, X and Y belong to the same coset. X and Y belong to the same coset. So we have now proven from left to right, the only if case. All right, so that's the end of the theory. Now we're into the problem-solving part, which I've merged with the last part of the theory. All right, so question 1, 3, and 5, which is half of them. Okay, now this it's almost a theorem. The textbook writers, Barnard, is that his name? Barnard, yeah. So Barnard could have easily put this question, this problem, into the theory section because it's quite a substantial result, and it's the following. I've drawn it here in terms of Venn diagrams, so it's easier to understand. So the usual, you've got a set, a group G and group H, and you've got a homomorphic mapping between the two of them, between G and H. You've got a subgroup, right? S, subgroup of G. Yeah, S is a subgroup of G. And what's T? T is defined as the subset of H that gets mapped to by every element in your subgroup S. So all your points here, your Venn diagram, all your elements in your subgroup S, they map into this T. T by definition is your image set, if you like, of S, this subgroup. And you're asked to prove that this T, this subset of H, is actually a subgroup of H. Right? So show that T, this subset here, show that T is a subgroup, right, of H. Okay? So now we've done something similar to this before in proving that the kernel is a subgroup. So it's somewhat similar. So that's probably why it's in the problem session rather than in the problem at the back of the chapter, end of the chapter, rather than in the theory, because it's fairly similar to the proof that the kernel is a subgroup. All right. So as usual, to prove anything to be a subgroup, you have to show that that subset has the three properties: unit, has a unit, is closed, and has the inverses. All right. So let's show that this T has the unit of H. Right. Well, we know that if you map the unit of G, it will map to the unit of H. Right. That was one of the theorems we've done recently. Units with homomorphic mappings, a unit from G maps to the unit of H. So we know this is true. Okay. Now from that, that means the unit in G gets mapped into T. Why is that? Well, what is T? Oh, just a minute. No, let me say that again. This unit here, it's the unit of G, but it also belongs to S. Why is that? Well, because S is not just a subset, it's a subgroup, right? And therefore, as a group, subgroup still a group, it must have the unit. And now there's only one unit in a group, so that the unit of S here is also the unit of G. Okay? So that unit belongs to S, and it gets mapped into T. Right? Anything in S gets mapped into T. That's what T is by definition. Right? So therefore the unit of H belongs to T. Why? Because the E of G that you map from is in S, right? So we now, since the F of the unit of G belongs to T, now F of the unit of G equals the unit of H. Now, if this belongs to T, therefore this belongs to T. Right? So we now know the unit of H, the unit of H belongs to T. Right? So we have the unit in this subset. So we've done one of the three. Okay? We've shown the unit belongs to T. All right. Now let's try closure. And what do we mean by that? That means that any two elements in T, when you binary operate on the two of them, you form their product, the result will also belong to T. Right? It's closed. The binary operation is closed. All right? We'll let X and Y be any two elements belonging to S. Right? Now S is a subgroup, therefore it's a group. Therefore XY, the product XY, must also belong to S. Right? Because S is a group, so S is closed. Okay? So XY belongs to S. Yeah? See, S is a subgroup, therefore you have closure of S. Right? Now, if x and y belong to S, then f of x and f of y must belong to t, right? Because everything in S maps to t. Okay, so f of x and f of y belongs to t. Now, so we now have two elements in T, 1, 2. So let's find their product and see if that result, the product, also belongs to T. Let's try that. That's the nature of closure. All right. So let's multiply these two. So fx times fy. Now f is homomorphic, therefore we can rewrite this as this. Okay, f of xy. Now xy belongs to S, right? Because S is a group, and that means that f of xy, f of this, also belongs to T. Why is that? Well, because xy belongs to S, right? This element here belongs to S. So if you f it, if you map that xy, it will belong to T, because all elements of S get mapped into T. Right? So f of xy belongs to T. Now, I've sort of skipped. If f of xy belongs to T, that's this, right? This belongs to T, and therefore this belongs to T. Okay?